Hey, welcome to this video about mechanical advantage, which is a concept that we are learning in the grade 8 classroom right now, in particular with regards to levers. There's a couple of students in my class that were having some issues with this, so I'm creating this video to try and walk through what mechanical advantage is and how to calculate it using levers and how mechanical advantage changes when fulcrums change on a lever. So what we have here in front of us is a first class lever. And before we start with any calculations, it's probably a good idea for us to discuss what mechanical advantage is. Mechanical advantage is just like it sounds. You've got something mechanical, like a machine, and it's giving you an advantage. It's allowing you to be able to do something for you. So by using this machine, you are getting something out of it. So as with any machine, there is an input and there is an output. The input is what you as a human being are putting into it, and we measure that using something called newtons. The output is with what you're putting in, what the machine is doing for you, and henceforth you are able to figure out what a mechanical advantage is. So let's talk about how to solve mechanical advantage. Now this first class lever that we have here, you are going to be pushing down on this side. So this becomes your effort here. This we know as the fulcrum, which separates the load and the effort, and then obviously we've got our load right here. Now let's put a, let's say this box or whatever that we're lifting here weighs 100 newtons. We know that in order for us to be able to pick that box up, we have to be able to exert 100 newtons plus 1 for gravity to lift that straight up. Now I wonder if we were able to calculate the mechanical advantage of this lever, what would happen? How much mechanical advantage does it give us with the lever the way that it is? So let me just erase some of these strokes that I just made, and then we will start to calculate what this is. Okay, so here's what we need to look at. We need to look at the distance of this arm. Okay, now notice that it's stopping right there where the fulcrum is. This is the effort arm. And then from the fulcrum to our load, this becomes our load arm. In order to solve mechanical advantage, we need effort over load, which is a division sign. So we're dividing effort arm, the length of the effort arm, over the length of the load arm. So let me just arbitrarily throw some numbers in here. This is about halfway in the middle. So this kind of line right there kind of splits that effort arm and load arm in the middle. So let's say that this whole board was 10 meters, which makes this side 5 meters and this side 5 meters as well. So if we take this effort arm and we punch it into there, and we take this load arm and punch it into there, we end up with 5 divided by 5. And that gives us 1. Now that means the mechanical advantage of this machine is 1, or 100%. So let's think about that for a second. That means the machine is doing 100% of the work that we're putting into it. Now that sounds like the machine's doing everything, but in this case it's not the case. So what if we had, I don't know, let's say we exerted 10 newtons on this side. We're inputting 10 newtons. That means that the load arm is outputting 10 newtons, so it's 100% of what you're putting in. So you put in 10, the machine outputs 10. Now if we look at that mathematically, if we put 10 newtons of force on this box, which weighs 100 newtons, we're not lifting that box up. 10 is significantly less than 100, and so therefore we need either more effort or we need to change up our lever in order for this to work. So let's flip over to the next one. What you can see here is I've moved the fulcrum. The fulcrum was in the middle, and now it's been moved over closer to the load. The load hasn't changed. We're still at 100 newtons. But what I have here is now I've extended the effort arm. The effort arm is longer than the load arm. So if we know that mechanical advantage is effort arm over load arm, let's say that the length of the board hasn't changed. Let's say that we've got a effort arm of, let's say 7.5, 7.5, and the load arm, so if we're starting from there, that's the effort arm from the end. So this is kind of important. If we were to do this, if we were to put all the pressure right there, for instance, that means we could only measure to where we're putting the effort. So it's very important that when you're doing this, that you make sure that you try to extend the length of the board as much as possible. Let's say that this one was 7.5 meters now, and let's say that this guy was 2.5 meters. So the distance from the fulcrum to the load, the end of the load arm, where the load is at, would be 2.5 meters. If we took 7.5 and we divided it by 2.5, we end up with 3. So 7.5 divided by 2.5 gives us 3. Now that means we have a mechanical advantage of 3 times. Now think about this for 1 sec. If we went back to this one, the fulcrum being right here gave us a mechanical advantage of 1, or 100%. If we look here and the mechanical advantage is 3, it means that the machine is doing 3 times the amount of work that we are putting into it. So let's throw some numbers here. Let's say, again, I put in 10 newtons. It's got a mechanical advantage of 3, so if I put 10 newtons into here, it's going to output 10 times 3 mechanical advantage. It's going to output 30 newtons. Now that's still not enough to lift this 100 Newton box, but it is getting us closer there. I'm still putting in the same amount of force. However, the machine is doing more work than I'm putting in. So let's look if we even adjust that even more. Let's put the fulcrum out here. So the fulcrum has been moved way down here, and you'll notice that this right about here, that's where we're going to measure from our effort arm. Now this effort arm, let's say that effort arm is now 9 meters. And let's say that this guy right here to the load is only 1 meter. If we're trying to solve mechanical advantage, that means we have 9 meters effort arm divided by 1 meter load arm, and we end up with a mechanical advantage of 9. Which means that when we put in 1 Newton, it's putting out 9. So the mechanical advantage in the machine is doing 9 times more work than what we're putting in. So let's think about whether or not we can make this work. If I put 10 newtons in, it's going to be multiplied, so it's going to do like a force multiplier of 9 times. It's going to multiply the amount of force I'm putting in by 9 times because the mechanical advantage was 9. And I'm going to get 90 newtons out of it. So you'll notice that based on where we were at this time, excuse me, this gave us a mechanical advantage of 3, and we got 30 newtons. This gave us a mechanical advantage of 1. I put in 10. It outputted 10. You can see that moving the fulcrum closer to the load is going to allow us to have much more force. Now, one of the students in my class said this is a result of leverage, or he called it leverage. However you want to pronounce it, tomato, tomato, potato, potato, it doesn't matter. The idea is that the concept is the longer we make our effort arm, the more power we're going to be able to get out of this lever, and it's going to be able to allow us to lift things up. So I'm going to draw this out one more time, and let's look at 3 different calculations. I'm going to make this one mechanical advantage red. Okay, I'm going to make this guy, let's go greenish. So let's go green, or greenish. I don't know why my green's not rotating around. So I'll make it yellow. So then we're going to do a yellow, and then we're going to do a, let's say, a blue. So let's grab blue there. Okay, now I'm going to solve all these calculations using these colors to try and give us kind of an idea about what it is that we're doing here. So we know that our load was 100 newtons. So I'm just going to put that there for a second. We know that the load weighs 100 newtons. And if it weighs 100 newtons, then we have to be able to exert enough force to lift up that load using this. I'm just going to extend that out a little bit more. So let's switch to red here, and that's kind of right in the middle. So I know it's got a mechanical advantage of 1. So if I was to punch in 100 newtons times 1, I'm going to get 100 newtons output. It's only going to be able to balance that out. It's not going to be able to lift it up any higher because you're not accounting for gravity, so I have to add 1 for gravity. So if the lever was here, I'm looking at 100 newtons, 101 newtons for me to lift that up. If we switch to yellow, if I have 100 newtons, now we said that this one has a mechanical advantage of 3. So let's think about that for a second. If I took let's say 100 and we divided it by a mechanical advantage of 3, we're going to end up with something like 3.333 or 33.3333 repeating. If I was to add 1 more newton on top of that, then I end up with 34 newtons times 3, and I'll just do the math here real quickly. 3 times 4 is 12. Carry the 1, we get 102 newtons, and 102 is bigger than 100, so I know that if I put 34 newtons with the lever here, or the fulcrum rather, here, and still pushed on this end, but with 34 newtons, I have enough to lift up the load. So let's take a look at this last one, which is blue, and this one had a mechanical advantage of 9. So that's a mechanical advantage of 9. If I took 100 and divided it by 9, I end up with 1. That is there. I'm going to have 10. It's going to be another 1 and a decimal. So 11 something. So let's just, for the sake of this, let's just make it 12. Okay, I know that I would need 11 newtons. So let's make it 12, and I'm going to multiply that by 9. Mechanical advantage, because the machine is outputting with this fulcrum a 9. It's giving me a mechanical advantage of 9. 12 times 9, if I look at, well, 12 times 10 is 90, and 2 groups of 9 would be 18, so I'm looking at 118 newtons out of that. That's way more than the 100 newtons that I need for this. So notice the difference as the fulcrum moved. This one gave me a mechanical advantage of 1, and I had to input 101 newtons to lift the box. This one, I moved the fulcrum over closer to the load. It had a mechanical advantage of 3, and I used a third of the energy that I needed for this. Okay? And I was able to lift the box. Now this one, I used 1/10 of the energy, and I was able to lift the box with this mechanical advantage. So I'm hoping that this video kind of helps clarify what it is that we're doing and the concept of moving the fulcrum closer to the load to be able to do less work, working smarter, obviously, not harder. If by chance this video doesn't help you with that, please drop me a line in the comment section and I will try to explain it in a different way. And if you're in my class and watching this video, feel free to email me or touch base during science or any other time during recess or whatever, and we can kind of help clarify how to solve mechanical advantage before moving on to mechanical advantage of pulleys. All right, that's it for this video. Thanks for tuning in. If you have any concepts or something like that in science or math that you want to see, drop a line in the comment section and we'll make sure that it's taken care of. Thanks.